Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. In this video, I'll be answering question 4 of the 2020 Board of Studies Extension 2 trial paper, and this is a continuation of a series where I'm systematically working through all of the questions on this paper. So here in question 4, we're told to consider the polynomial px equals x cubed plus ax squared minus bx plus c, where a, b and c are positive constants. The graph of y equals px has stationary points x1, y1 and x2, y2 in the first and second quadrant respectively. Which diagram could represent the location of the roots of px in the complex plane? And we've got 4 options here. Notice that in all 4 options there are 3 solutions, which makes sense because we're dealing with a cubic. In all of them, there's 1 solution that is real and 2 solutions that are complex, so that's interesting to note. And I think it's consistent with the facts that we're given. So really what we're choosing between, if you look at these 4 options, is whether the real root will be have a positive or negative x value, and then what's the nature of the complex roots. And basically through making deductions on those 2 concepts, I think through a power of elimination or process of elimination, we can get to the right answer here. So if you do find my explanation helpful, please be sure to give it a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, be sure to subscribe to my channel so that you can stay in the loop. So what I've done here is I've just written up the polynomial that we're dealing with and noted the 2 turning points being in quadrant 1 and 2 respectively. I've drawn up our 4 options here because basically we're going to use a process of elimination, so it's helpful to kind of cross out options as we work out they can't be correct. And then I've drawn up a Cartesian plane here because I think it might be helpful just to draw up this polynomial based on what we can deduce, because that'll help us in kind of working out what must be right or wrong here. So in this Cartesian plane, I should note that the quadrants, to number the quadrants, we actually work in this anti-clockwise direction. So we have quadrant 1, quadrant 2, quadrant 3, and then quadrant 4. And we're told that the turning points, we know there'll be 2 turning points because if you differentiate this, you get a polynomial with power 2. Those 2 turning points are here in quadrant 1 and here in quadrant 2. The other thing we can know about this cubic is because there's a 1 in front of the x cubed, we can call it monic. Basically, we know that as x comes to negative infinity, the power of 3 will maintain that negative, so the polynomial will come to negative infinity, and conversely, as x goes to positive infinity, the cubic will go to positive infinity. So I know that in essence, when x is 0, we're going to have c. It's going to cross at some point c, cross the y-axis. And essentially the cubic will look something like this. And these are our 2 turning points. So I know this point here would be x1, y1, and this point here would be x2, y2. And so this is y is equal to the polynomial px. Now I think the reason, or the reason I think drawing this up can help us a little is we can see that the real root, there's going to be 1 real root, which is made clear by all of our options. It crosses the x-axis when x has a negative value. So right away we can take a look at the various options given to us and strike out those that have the real solution in the positive x space, because we know the real solution will be negative. So I can cross out A, since the real solution here was positive, and I can cross out C, since that real solution was positive. So that's good. We've now reduced this question to a flip of a coin. Now, the other thing we know about the roots of polynomials is that to the extent there are complex roots, they will be complex conjugates. So complex roots always come as complex conjugates. So now all I need to do is look at B and D and see that in D, these aren't conjugates of each other. In other words, they're not kind of mirror images around the real axis, where in B they are. They take the same x value, real value, and they're equal and opposite magnitudes in the y value, the imaginary plane. So without even doing any further work, I can know that D cannot be correct, and therefore B must be our answer here. So in the end, this question, I think, is fairly straightforward. It just requires you to methodically make use of what you know, because it's one of those questions where you're not given the actual polynomial. The A, B, and C are just generic. So you can't actually do the algebra to work out the solutions. You have to kind of stick with the conceptual ideas. But really there were just two ideas that we had to make note of, where the turning points were, so that we could kind of sketch just generically what this curve would look like, so that we could see where the real solution was. And then knowing that complex solutions always come in conjugate pairs. With those two pieces of knowledge alone, we could use a process of elimination to get to our answer. So hopefully that made sense, and having now seen this approach, you could apply it yourself if you ever came across a similar question. So yeah, hopefully that was all helpful for you, and tick boom.